Welcome to an in-depth exploration of the nebular theory, focusing on the formation and structure of our solar system. Let's dive into the cosmic processes that shape the planets and stars. By the end of this lecture, you'll be equipped to describe the structure of a protoplanetary disk, explain the temperature gradient and condensation sequence, understand the formation of rocky versus gaseous planets, and identify limitations of the classical nebular model. Previously, we discussed the collapse of molecular clouds, the formation of protostars, disk formation, and angular momentum conservation. Now, we explore how different types of planets emerge from these processes. The protoplanetary disk is characterized by a central protostar, a surrounding rotating disk, a dense mid-plane, and a temperature that decreases outward. These features are crucial for planet formation. Temperature plays a vital role in the protoplanetary disk, with the inner region being very hot. This gradient controls which materials can condense, influencing the composition of emerging planets. Different materials condense at varying temperatures, affecting planetary composition. Metals condense at high temperatures, silicates at moderately high, and ices at low temperatures, shaping the planet's makeup. The snowline marks the distance from the star where volatiles condense into ice, defining regions of solid matter availability. Beyond this line, planets grow faster, impacting their development. In the inner disk, high temperatures allow only metals and silicates to survive, leading to the formation of small, dense rocky planets like Mercury, Venus, Earth, and Mars. The outer disk's low temperatures allow ices and rocks to form larger solid cores quickly, which attract hydrogen and helium, resulting in the rapid formation of gas giants like Jupiter and Saturn. In the cold regions beyond gas giants, ice giants like Uranus and Neptune form from ices with less gas envelope due to reduced gas capture and colder conditions. Inner planets are smaller due to limited material and high temperatures that vaporize ices, resulting in rocky planets with less solid material available for formation. Understanding the imbalance in angular momentum distribution is crucial, as most of the mass is in the Sun, yet the planets, especially gas giants, hold most of the angular momentum. Observations of protoplanetary disks, consistent planetary orbits, asteroid and comet predictions, and computer simulations all support the nebular model, confirming our understanding of solar system formation. The classical nebular model faces challenges like angular momentum distribution, planet migration, high orbital eccentricity, and unexplained phenomena like super-Earths and hot Jupiters, necessitating further research. In summary, planets form from a rotating disk of gas and dust, with temperature determining material condensation. While the classical model explains much, challenges remain, highlighting the need for continued observation and modeling.